Okay. um, okay, so this is about Monte Carlo methods. And so this one, actually, I have a lot of stuff in it. But so what I'll do, I'll go through, this is the subgradient or stochastic subgradient algorithm, or stochastic gradient, which is what people call it in machine learning. This has become really the biggest algorithm in machine learning. It's the method that everybody uses. I think many of them don't realize that it comes from stochastic programming. That it was Shor, it was Noam Shor, well, Boris Polyak in Russia, and then Noam Shor in Kiev, who really started it. Yeah. There's, Pnishny, there's a number of people. So I'll talk about these methods. I'll talk about some convergence results. There's a sort of the most basic approach that you can think of is you just take samples and use that as your distribution. And that's often called sample average approximation. So I'll talk about some of those convergence results. Some other convergence results which have optimality tests. So you test for convergence. But one thing that you have to be careful with is if you test multiple times, you may have early stopping. So you may randomly test and come up with a positive result. And that leads to early stopping. And that's common in a lot of applications that people use now. A/B testing is a big thing on the internet or for internet kinds of applications, where you try one thing, you try another thing, you see which one produces the best results. But that's susceptible to early stopping, early termination. And so I'll talk about some of these convergence results to avoid early termination. Another link to different parts of mathematics. This involves the Riemann zeta function. So this is kind of an interesting result. And then I'll mention a little bit more about the cut sampling methods that I mentioned yesterday. And then this other approach, which is a sampling method that's applied like the decomposition methods, that's often called stochastic dual dynamic programming, or SDDP. So I'll mention those methods as well. Okay, so as I say, it's a lot of things on this topic. So so I sort of divided it up into three parts. The stochastic gradient or stochastic approximation type algorithms, they started off just being approximation algorithms, like that you're just trying to approximate some you're trying to approximate the state of some system, and you don't know exactly what state it's in, but you're getting observations, and you want to come up with an estimate of the state. That's like minimizing the distance of what your estimate is from the truth. So that's another kind of stochastic optimization problem. But in the optimization context, it's called stochastic gradient or stochastic subgradient or stochastic quasi-gradient. But the basic idea is you sample a descent direction, you move in that direction, and there are certain convergence results. The other idea is that you take a lot of samples, and then so in this case, you just often take one sample. So every time you get a new observation, you make a step. Or another thing is that you could collect a lot of observations together and then optimize over those observations. That's called sample average approximation, or SAA. And there you solve the sample problem that includes all of your observations. And you can also think of this as applying to these multi-stage problems. This is that SDDP, the Stochastic Dual Dynamic Programming approach. And then I'll mention these other methods called stochastic decomposition methods, where you sample cuts and you make them increase the precision over time. So as the algorithm goes along, you get finer and finer precision. Okay, so as I said, Boris Polyak, who just celebrated his 80th birthday, I think. I think he also just, what's that? P-O-L, yeah, this one, not Ed Pol, oh, this is Boris Polyak, yeah. Yeah, that's right. There's also Ed Polak. Yeah. There's Ed Polak and Boris Polyak. I think he's the first to really specify what the subgradient algorithm is. So the general setting, this is the general optimization setting. The general optimization setting is you minimize a function f for x in a convex set, and all it requires is that you can find a subgradient. So you find any subgradient of the function f at a point x. So you just need an oracle that determines the subgradient. And it doesn't have to be any particular subgradient. It's any subgradient of the function. And then what the algorithm does is it's minimizing. So it takes a step in the negative subgradient direction, and it specifies as the step size. So the step size here is sk, and that's it. You specify what steps you're going to take. So the step sizes are determined a priori. You're not optimizing over them. You're just given a sequence of step sizes, and you follow that. And then what the algorithm does is it steps from the current iterate in the negative subgradient direction a length sk, and then you get a new iterate. This is either this is always in x, in other words, this is always feasible, or you project it. So it would be the projection onto the feasible region of this step. So you take the projection of this onto the feasible region, and then you get your step. Okay, so here's I'll go through the proof just to, I'll go through what the proof involves and what the assumptions are. Okay, so first let's just assume that there is a minimum. So we have a minimum value. In other words, it doesn't, either it's not infeasible and it doesn't go down to minus infinity. F is Lipschitz continuous, where Lipschitz constant here is m. So the difference between the function values at any 2 points is less than or equal to m times the distance between those points. Now here are the conditions on sk, and almost all these algorithms have this, that the sum of the step sizes has to be infinity. And the idea of that is you have to be able to get to any point in the space. So the sum of the step sizes can't have a bound. Otherwise, you won't be able to get to any of the points in space. So the sum of the step sizes is equal to infinity. And now this is the key to having this work. The sum of the squared step sizes, however, is finite. So what that means is that basically sk has to look something like a harmonic series, like 1 over k. So it's something like 1 over k, where the sum of 1 over k is infinity, but the sum of 1 over k squared is finite. Okay, so you specify a sequence of step sizes like this, and then the result is that for any epsilon, you can always get within epsilon of an optimal solution for every iteration bigger than some finite number. So in other words, the limit of the f at your iterates xk is going to be the optimal solution. So that's the convergence result. So now I'll show you basically how it works, just to give you why this is true, to give you an idea of how these proofs all are constructed. Ooh, boy, that's going to be hard to read. Okay, so here's the idea. We're going to use convexity. So we have that this eta is a subgradient. So that means that if I take f of x star plus eta times x star minus k, that's greater than or equal to f of xk. Or the difference between the value of f at its optimum and at any iterate is greater than or equal to the subgradient times the difference between the optimum and the iterate. Okay, now from Lipschitz condition, so Lipschitz condition states basically that the norm of the subgradient is bounded. So that's bounded by the Lipschitz constant. So the norm of the subgradient is at most whatever that Lipschitz constant is. Okay, so now So now let's suppose that we have a subsequence that converges. So just suppose that there's some subsequence that converges to a point here. And so this is along this subsequence. And let's suppose the opposite of what we're trying to prove. So let's say that there's a convergent subsequence and the value of f at the limit of that convergent subsequence is strictly greater than the optimal solution. So if the value is strictly greater than the optimal solution, then what we want to do is show that there's a contradiction. So we're going to assume that it's the value at that limit point along the subsequence is greater than the value at the optimal solution. Okay, so then that means it's greater than the optimal solution plus some epsilon, and that has to be true for any epsilon that's positive, and that means for all of the points along this subsequence, what we must have is that f at the value of f at the points along that subsequence are at least as great as the optimal solution plus epsilon. So we've got this inequality over here. Yeah, minimize. What's that? Yes. Yeah, I'm assuming. Yeah, x star is optimal, but I'm converged to something that's non-optimal. So I'm assuming I'm assuming that I don't converge. So I'm assuming the opposite of the conclusion. Yeah, so I'm assuming the negative of my of the result I'm trying to prove, and then I want to show that there's a contradiction, so that it must be that actually this does converge to this. So I assume it's positive, and then what I'm going to show is if I assume that it's positive, I get a contradiction. So if I assume that it's strictly greater than the minimum, then I'm going to get a contradiction. And when I make that assumption, what that means is that along the subsequence, eventually, every single value along the subsequence has to be bounded away from the minimum. So eventually, every point along the subsequence is bounded away from the minimum. Okay, so here's the way the contradiction is constructed. Well, let's take a point at in a single iterate. Let's say the iterate is xk plus 1, and take its distance from an optimal solution x star and square that. So this is the difference between, this is the norm squared distance between the iterate xk plus 1 and the optimal solution. All right, and then I'm just rewriting it over here. So I've got, it's the difference between the point at xk plus 1 and the optimal solution, the point at xk plus 1 and the optimal solution, and then what I've done is I've just added and subtracted the previous iterate. So I just put that in here. I mean, this is 0, but I just subtracted the previous iterate and added it back. Subtracted it and added it back, and then what I'm going to do is I'll take, so this would be my step size on the this is my step on the previous iterate. It's this iterate minus the previous one. And then this is however far the previous iterate was from the optimal solution. Okay, so I write it down this way, and now I substitute. So this was basically how far I stepped. Rho here is the step size in this case. So this is how far I stepped. I stepped minus rho k in the subgradient eta k direction. And then xk minus x star, that's how far I was in the previous iteration. Okay, so then I have, okay, so that was how far I was in the previous iteration. Now I just multiply this out, so I've got rho k squared times the norm of the subgradient squared, and then minus 2 rho k times the difference between xk and xk star times eta k. And then the distance that I was away from optimal on the previous iterate. All right, now this part, I'm just going to use this subgradient inequality up here. So eta k times xk minus x star, it's like flipping it on the other side, that is less than or equal to f star minus f of xk. All right, so this, this is, I have minus eta k, xk minus x star is less than or equal to, yeah, it's the same as minus xk minus x star. That's what's up here. So this part, that's this right-hand side over here, is less than or equal to this left-hand side down here. Okay, so now I have this, which is now the step size squared times the norm of the subgradient squared, plus this term, which is the difference between the optimal value and your previous iterate value. All right, now I'm saying that the difference between the optimal value and the previous iterate value, this is strictly negative, right? Because this is, I'm subtracting off something that's bigger than this. I'm saying that this value, f of xk, is strictly bigger than f star. So this would be something negative. These two things are positive, but this is strictly negative. Right now I just keep on repeating this, doing this for each of these xki's, each of the points that was along this sequence. I keep on doing this I keep on expanding xk minus xk star squared for each of the points that's along that sequence. So I get the sum of all the terms that look like this all the way down to k. So I get the sum of all of those. And then I'll get something like this. So I'll have the sum of the step sizes squared times the norm of the subgradient squared. And then I'll have 2, and now I've got the sum everywhere along this subsequence for all the points ki up to k of the difference between the optimal value and the value along that subsequence. And then I'll have however far away I was, however far away I was at the very beginning. So this is, I know this is, now I know that this is an upper bound on whatever this value was. And then I can write this value out here. Well, this, I know that this value I assumed was f of x star minus f of xk is less than or equal to minus epsilon. So this is at most minus epsilon. That was my assumption up here when I made this contradiction. So this is at most minus epsilon. So I put that in here, and now I've got the sum of the step sizes squared times the norm of the subgradient is at most m. So this is at most m squared. That's the Lipschitz constant. And then this is the distance that I was from optimal at the very beginning. Well, this is finite. This, because I assume this sum of the squared step sizes is constant, or is finite. So the sum of the squared step sizes is finite. So this is finite. This is finite. But now as k increases, this is unbounded. So this goes to minus infinity. So I have finite, finite, and minus infinity. This whole thing is minus infinity. And that's impossible because it has to be greater than or equal to 0. So, so that's the contradiction. So the way to prove these is, it's a little bit different from proving a lot of other kinds of optimization methods. We're not showing strict descent on every, iterate, which is what you often do in optimization. We just know that eventually all the iterates, if I know that I have to get some kind of descent relative to, because of the convexity. So I have some kind of descent relative to the value before because of convexity. But the main thing is that if I'm not converging, that I get something that leads to basically an accumulation of an infinite amount of losses. And I can't have an infinite amount of losses. So the fact that here's the rho k's. The rho k's are going to sum up to infinity, and they multiply by epsilon. That gives me something that's minus infinity. That gives me the contradiction. Okay, so the way to prove these kinds of results is that basically you do an expansion on the distance that any point is from an optimal solution, and then show that because that distance has to be greater than or equal to 0, that you're going to be able to construct a contradiction by expanding out that distance, and then seeing how it relates to the iterates that you have on each of the different steps of the algorithm. Okay, so that's why subgradient works. As I said, it's often from stochastic approximation. Two people who worked on this a lot, Harold Kushner and then Dupach, whose wife, Dupacheva, was also a stochastic programmer. I guess it sort of started with Robbins and Monroe in the 1950s, and then Kushner and Dupach did a lot of work showing convergence and showing how fast these kinds of methods converge during the 60s and 70s. I would say the stochastic programming group is kind of focused around Yermolyev. Yermolyev is also part of that Russian group. And he called it stochastic quasi-gradient because you don't even need exact subgradients. All you need are things that eventually are close to subgradients. So he noticed that you could actually have a lot of error at the very beginning. As long as they're errors are getting smaller and smaller over time, as long as those errors get smaller and smaller over time, you still get the same kind of convergence results. And he expressed it in very general terms, saying you could optimize any kind of function subject to, well, any kind of convex function subject to convex constraints. You can always, when your iterate is outside of the boundary of your feasible region, you can always project it back. So whenever you get an iterate that moves from here, xk, say, up to here, you can always get a projection back onto the boundary and find another feasible point. So he kind of generalized all these subgradient methods as well. So this is just the stochastic gradient. All we say is that the expectation of those steps, those here I was calling functions eta and subgradients beta, but the expectation of those steps may have some error. So there may be some error in terms of whether it's a subgradient or not. But as long as that error goes to 0, then you can still get, as long as it goes to 0 at a given rate, you still get the same kind of constraints. This is showing how it works in the two-stage model. So the iterates are something like this: projection onto the feasible region, take a step, and this would be the objective subgradient, negative objective subgradient direction, or quasi-subgradient direction. And so if I were to solve this two-stage model, the two-stage model, my x would be the set of constraints that x has to satisfy in the first stage, so like ax equals b and x non-negative. Let's say this is my objective, and then this is my objective in x, and then my objective, or my first stage objective, this is my objective in x for the recourse problem, and that what I'm integrating over is the second stage objective. So the second stage objective is that I optimize with respect to these constraints. And so I have my subgradient direction in the second stage would be given by a multiplier here that gives me the optimal value. So whatever the dual variable, so this would be like the dual variable for this problem. And that would be, it has to be feasible. So I would take a sample of this problem, find its dual variables. That would be the dual variables associated with this constraint. Those dual variables times the right-hand side give me the objective value. And then this would be the step. That's where I would step. So I would step in the negative of this direction, and then project back onto the feasible region, and then take another sample, find the dual variables, project it on the feasible region, and then keep on doing that. I think I'll, yeah, so this is why this is basically the same argument, but this is with the subgradient term. So I can construct the same kind of argument as I had before, and what I want to do is to show that I get a contradiction, that this greater than or equal to 0 is going to produce a contradiction. So I'll again get a terms like this, where they're multiplying the step length squared. So this part, I think this part should be finite, because step length squared is finite. Any original distance is finite. And then the only question is, yeah, so this part, the fact that if I have a contradiction that I don't have convergence, then this part is going to go to minus infinity. So I have to, this part is finite. This part is finite because this subgradient again is going to be, or this distance is always going to be bounded. So these two parts are always going to be bounded. Yeah, so these two parts are always going to be bounded. And then the question is, what happens with this? This summing up this part of the time series, I have to, or this part of the sequence, I have to somehow bound this. And to bound this, you use a result of Kolmogorov that's called the 3-series result. And it says that this is a random series in here. But it says that a random series like this is the random component that I want to make sure is finite. So if I can make sure that this is finite, then I'll get something finite. And it says sum of this sequence converges almost surely if and only if there exists an event, there exists a value A such that the probability that x is greater than A is finite, or that x is greater than A is finite, that the expectation conditional on A is finite, and that the variance is finite. So as long as I have, so basically what this says is as long as I have finite variance, this Kolmogorov theorem says that this term is bounded, or this the sum of these components is finite. And if the sum of those components is finite, then I get this contradiction. So the only difference in the stochastic part is I have to worry that there's a stochastic part of that sequence, and whether that converges almost surely. That's the part that I need. I need that stochastic part converges almost surely in order to prove this. Okay, but that gives you the stochastic convergence. And as I said, you don't even need exact subgradients. You just need things that are close. So this is formally what the assumptions are. It's convex, continuous, convex, compact. That's compact is just so that we know that there's always a subsequence that converges to something. Yeah, and then we have a set of parameters. This is like these would be like the minimum dot product between the subgradient of the objective and any steps that we take in the set. So basically this is going to be bounded if my subgradients are bounded. So it's a little bit more general, in fact, than Lipschitz continuous. And all these things are satisfied with probability 1. The sum of the steps is infinite, and the sum of the steps squared times the norm, this would be the norm of the subgradient squared, plus the norm of basically this inner product, all of that is bounded as well. And then you get the convergence result. Oh, wow. Well, this is kind of showing, examples of this would be like the x. So in the subgradient methods, x moves around. So this is the true optimal solution here. And the x, as it's following the algorithm, it moves around where the true optimal solution is. In fact, it doesn't really settle down because those step sizes until those step sizes get really small. your samples of the objective, because every time you're sampling the objective, it's something different. They're never calming down. They're always random. So you always have samples of the objective that are have some variance with them. So you have to keep track of what the mean of the objectives are, but the samples go up and down. The point of showing this is that it's not always obvious how you tell whether this is converged. So one of the challenges is to be able to say, oh, this is converged to something. Because it's always moving around the optimal solution, and it takes a while, and it is a random method, so it's never going to converge in the same way for any sample path that you take. So it's always moving up and down around an optimal solution. Okay, so there are a number of things you can do with these. There's some algorithms that, there are a number of different adjustments. So there are methods called regularized methods that, for example, Yuri Nesterov has some procedures that accelerate convergence with regularization. Regularization is adding in like a quadratic term. So you add in a quadratic term to the objective, and often, if you do it in the right way, you can accelerate convergence. Yes, you add. Yes, yeah, you add on a quadratic term to get a strongly convex function. Yeah, yeah. So that's one way to accelerate convergence here. There's a lot of ways in which people adjust the step size dynamically, and a lot of people in machine learning often don't even adjust the step size. So for a lot of machine learning examples, people are using constant step sizes. The idea being, well, if I keep it constant for a while and then I reduce it, that it should still be okay. You get a lot more movement when you keep the step size constant. But if you can still show some results even with constant step sizes that you get. You don't get optimality, but you get convergence to maybe a given range of optimality. So some people have been doing that, particularly in machine learning examples. There are different ways to test for convergence. Like I said, this is kind of tricky. And ways to get confidence intervals. So you have to do some kind of sampling that's separate from the optimization. So that's kind of a challenge as well. So how you do some other kinds of sampling in order to get these to work. And then particularly again for machine learning. So one of the reasons actually these work pretty well is that they don't overfit too much. That is, what you don't want is that particularly in machine learning problems where you have very high dimensions, so your dimension might be in the hundreds of thousands or 100,000, but you only have maybe 10,000 observations. So you have a higher dimension than you have observations. So you'd be very prone to overfitting because you have so many different variables that you're working with. Subgradient is actually pretty good for that because it's not very precise. You're not converging, you're converging quite slowly to a true optimum, but you're always improving. And so by always improving, but maybe never getting to the true optimum is going to be overfit a lot. But these intermediate outcomes may not have as much overfitting, so they may be better. So that's kind of well, it's sort of a natural advantage of stochastic subgradient. Okay, so this is about that algorithm. Let me talk a little bit about some convergence rates, in particular, that are good. Oh, here, that's, yeah, okay, this is one of my papers in JOTA. I was trying to, I think I have a few papers in JOTA. So this is a paper with Dai and Chen. So there are a few papers that I'll mention that have some convergence results. So this first paper by Alex Shapiro and Tito Homem de Melo, and then this paper by myself, Dai and Chen, and then a paper by David Morton. So as I said, one of the most common Monte Carlo approaches is that I just sample, here I have samples again are omega. I just sample the random values, and then I'll take my objective. Here my objective is G. So I'll take my objective with those sampled values, I'll average that, and I'll optimize over that. So this is just the sample average of the expectation objective. And then the question is, if I have a solution to that, let's say x n prime here. Let's say that's the solution to this sample average problem. What I would like to say is that I'm not too far away from an optimal solution. So if x star is the set of optimal solutions, I'd like to say that the distance between the sample average solution, x prime n here, is not too great. So I'd like to show that, in fact, I'd like to show that the distance is 0 for some value of n. In particular, what is shown in the Shapiro paper is that for discrete distributions, there exists an n star such that with probability 1, if you have more samples than n star, then you get an optimal solution. So you get an optimal solution exactly if you take enough samples with probability 1. Okay, so this is kind of formally what the statement is. Let's suppose that there's a unique optimal solution. So I have a unique optimum. So f is my so I made f be the expectation of g. Okay, so here f satisfies. It's not quite the strong convexity, but f is bounded away from, or f of x at any point that's non-optimal is bounded away from the value of the optimum value by something at least linear in the distance. So what that says is that it has, I don't know if I can, too much space to draw, but it says basically that around x star, it's a little bit sharp. It's got to be sharp enough by c. So I can't have basically gradients that converge to 0 slow, or converge to 0 down here like that. They have to come in at an angle and hit the optimal solution. So that's relatively strong, but it turns out that's okay for linear programs. Okay, so for linear programs, this is going to be okay. So if I have the two-stage stochastic linear program and this assumption, that's okay. That's with a finite distribution. Okay, so the first result is if G is convex and X is compact, F is finite, and I have this assumption, then with probability 1, this does happen. So there is some value such that if I have enough samples, then I converge to an optimal solution. Okay, and then the second result is if my set of outcomes is finite, and I have piecewise linear and convex function G, and if X is polyhedral, so X is given by a set of linear constraints, and it's non-empty and bounded as well, then the same kind of result, except now I didn't have to assume a unique optimum here, but I get convergence with probability 1 to some point in fact, it's some point on the face of the set of optimal solutions. So on a lower dimensional support of the set of optima. So basically, either way, what this says is for a finite number of samples, you get convergence to an optimal solution. Now, effectively, both of these assume that I have a finite set of realizations, because in order to have this result up here, I need a finite set of samples. I can't, because like I said, I have differentiability if I have a continuous set of random variables. So this says if I have a finite set of random variables, then that's going to be true. Okay, so here's another result. If G prime's directional derivatives, so its derivative in the direction t, if that's bounded, basically for any t, and for any realization of a random variable, then we'll get some other results. So under the assumptions before, and this result here, then eventually the probability that the distance is 0 is converging exponentially fast. So the log of this probability over n is converging down to 0 exponentially fast. Oh, thank you. Okay, so they have two sets of results. One is that you can have a finite number of samples and you get exact convergence. And just in general, if I add in something like this, these bounded directional derivatives, if I add in these bounded directional derivatives, then I get that finite convergence as well. Or I get exponentially fast convergence. That is that the log of the probability is decreasing with beta over n. So decreasing by something proportional to 1 over n. Okay, so this is a result in my paper with Dai and Chen. And this says, okay, so if I start off with a point that's close enough to an optimal solution, no, with Newton's method, yeah, you have to be close enough, right? Yeah. Yeah, it's hard to know where you can start. Well, yeah. So, well, this one, actually, this one I don't have to, as long as I get all these assumptions in here, I don't have to assume anything about the starting point. But there are a number of different assumptions. So there's assumptions that this is the set of gradients or subgradients. The subgradients are bounded by something that is well, it's bounded in the it's bounded in essentially like this Laplace transform. So it has a bounded Laplace transform. That's what this basically says. So the expectation of the exponential of some parameter theta times that value times this function here, that's bounded. And now, then this is actually for all x. Okay, so if I have this assumption, which is a bound on the subgradients, so it's in particular this is always satisfied if it's Lipschitz continuous. But even if it's not Lipschitz continuous, as long as these subgradients are bounded in this particular way with this Laplace transform that's bounded, then again, for any epsilon, there exists an A and a B, such that the probability that your objective function after n iterations is greater than the optimal solution plus epsilon is decreasing exponentially in n. So it's less than or equal to this alpha times an exponential of minus beta times n. If your solution is unique, then I can also, so if the solution is unique, then I also know that the solutions are converging to an optimal solution exponentially. Yeah, and I can show that this yeah, this should be the same thing when it's discrete. So this basically says you get convergence of the function values and you get convergence of the solutions exponentially fast in n. And in fact, you can explicitly come up with those these coefficients, like this alpha and the beta. So for particular values of the objective function, you can explicitly write down what these functions are, and you have exponential convergence. So that's the most important part of this. Is it's going down exponentially in the number of samples. Okay. So one of the questions here is like, so how, you know that these things converge, but how do you test how fast they're converging? So you could sample from the set of subgradients. Let's say g is the function I'm looking at. I could sample and get sample expectation, and then say, well, what's the probability that at my current iterate that the expected value of the subgradients are actually less than epsilon? Well, and I would like to, if that probability is greater than or equal to alpha, then I would like to say, okay, I am alpha % confident that I have, well, at least I have small subgradients. So that's like being alpha % confident of having, well, that would be alpha % confident of being within epsilon times a Lipschitz constant of an optimal solution. So if I could show that, if I can show that the subgradients are all less than epsilon, and I know that there's Lipschitz constant of m, then I know that I'm no farther than epsilon times m away from an optimal solution. Yeah, so otherwise I'd take a step. So the problem with, if I keep on doing this, then what may happen is that I'll get a random observation of what this expectation might be. I'll get a random observation that's too low. So I'll just randomly say, oh, my algorithm tells me that I've got convergence, but I really don't. It's just because I'm sampling, testing again. And if you randomly test something, you have a 1% error rate. In other words, 1% of the time it falsely tells you that you've stopped. Then eventually you're going to stop, but even though you've never gotten there. So you really have to, in order to use sequential stopping like this, you have to increase the precision that you use to judge whether you stop or not. So you have to increase the precision each time you do that. So that's a result. So I have a result from David Morton here about doing that. So suppose for example, I've used nk samples on iteration k, and I've got an upper and a lower bound on my objective function. And let's say that difference is dk. And now suppose I had an algorithm that just said, okay, if my upper bound and lower bound get close to one another, then I think that f has to be at an optimal solution. Because if upper and lower are equal, then they must be the minimum. I can't do any better. So I might iterate until I find a difference between this upper and lower bound that's less than or equal to 0. So t might be the infimum over the times k when dk is less than or equal to 0. Now what I would like is that if I terminate this way, I would like to be close to an optimal solution. Well, if I just keep n fixed all the time, then the probability that all of these values are positive when I stop the probability that I get a bunch of values that are positive is very small, which means the chance of stopping is very large. That you're going to stop even if the value here is always positive. So in other words, if I always have an error, I'm eventually going to stop, even though the error is still there. So I'm never going to get convergence. So it's if you just keep n fixed all the time, you'll never actually converge. So what you have to do is to increase the number of samples. So what he does in this paper is to say, okay, so let's say t is the point where you're going to stop. You're going to say, as soon as your upper bound and lower bound are close to one another, I'll stop. What I have to do is to increase my number of samples. Well, I'm going to have to use a number of samples that has values like this. It's going to be log of the number of trials that I make, the number of sets of observations. It's going to be related to whatever the variance of the objective is. So it's the variance of the objective divided by what my precision, what precision I'm seeking, divided by the epsilon squared, and then times a value beta plus 2 times another value p times the log of the number of samples, where this value beta has this expression here. There's a parameter alpha that's going to be, that alpha is a parameter that's related to what my confidence is of the confidence level that I want to have of stopping. So for this confidence level alpha, beta is going to be expressed this way, where this is the Riemann zeta function. The Riemann zeta function evaluated at a point P. So P's a free parameter here as long as it's greater than 1. So I could use any P that's greater than 1 because it's going to affect what beta is. So I could sort of trade off P and beta in this case. But the Riemann zeta function is the infinite sum of k to the minus P. So P is greater than 1, which means this converges. So it depends on how big you want to make P. So if I make P bigger here, then I get a smaller zeta of P. So this Riemann zeta function gives me a value of this parameter such that I can set my sample size so that the probability that my error is that I'm at most epsilon away from an optimal solution, the probability that I'm at most epsilon away from an optimal solution is at least 1 minus alpha. So alpha is like the error that I would allow. So if I want to have 95%, so alpha would be 5%, then I would put alpha of 0.05 in here, solve for what this beta should be, choose a value of P, and then that tells me how many samples I need on every iteration in order to guarantee that I'm 95% confident that I'm within epsilon of an optimal solution. So we can get, so as long as your samples are increasing, then you can use these kinds of stopping rules. I'll mention this other class of algorithms. There's another class of algorithms called stochastic decomposition that's due to Julie Heigl and Subhrajit Sen. And the idea of these methods is you do the decomposition method with samples, but the samples improve with the number of iterations. So I'll start off with, let's say, just one observation. So I just have one observation, maybe the mean of my recourse problem, and I solve that problem with the mean of the recourse problem. And then I'll take a set of samples and I'll update my value of the recourse function based on those samples. So this is just a sample average of what samples I take. I'll find the dual variables associated with those, and then I'll construct, so these are the same E's I had in the L-shaped method. I'll construct a cut from those using those dual variables. And then I add that cut into the L-shaped method in such a way that I decrease, so I decrease the emphasis of all the previous ones. So I make the previous samples, which are less precise, actually disappear. So I weight them less and less. So I multiply them by the previous number of samples divided by the current number of samples. So this makes the weight of those previous samples get smaller and smaller. So I keep on adding more and more precise cuts, and I decrease the weight on the previous cuts, and that gives me a convergence sequence as well. So the cuts improve as you have more samples, the old cuts drop off, and the limit points are in an optimal set. And there are different ways you have to, different things you have to do for convergence. Again, these iterates sort of wander all over the place, and the objective values wander as well, but eventually all the limit points are going to be optimal solutions. Okay, I'll mention a couple of results just on general sampling results. So this is that sample average approximation again. So here's the sample average approximation. I've taken new samples, averaged the function values for those new samples, and then I've solved for x. And what I'd like to do is to say something about the convergence of the x that solves the sample average problem relative to an optimal solution. In fact, what I'd like is something that's like a central limit result. So I'd like that the square root of the number of samples times the difference between the sample average optimum minus the true optimum. I would like to say that that converges to something that's like a normal distribution. So I'd like to find the convergence of this to an optimal solution, so that then what I could do is I could say, oh, now I can build a confidence interval. So when I have x new, I can build a confidence interval around it based on what I think this u distribution should be. I can build a confidence interval around it and know that that confidence interval includes the optimal solution. Okay, so I'll mention sort of the basic result here. So this is the result. So this is the result from Alan King and Terry Rockefeller from Alan King's thesis. And it says if G is convex and it's twice differentiable, X is a convex polyhedron, G has a gradient, so its gradient is measurable, and a Lipschitz, so it's also Lipschitz, so it has a Lipschitz constant that's square integrable. And yeah, so the gradient of G is this Lipschitz, is bounded by this Lipschitz constant. And then what it says is yeah, so this is true for any x1 and x2. So there exists a value where basically G has finite variance, and the norm squared of, and this is the norm squared of, or the expected norm squared of the gradient, or the expected square of the gradient. That's, yeah, which is semi-definite. Then we get one of these results. So here, so the solution of that sample problem converges to the true solution, again with the square root of the number of samples, where the asymptotic distribution of that is a random variable u, where u is the solution to this optimization model. So it's an optimization model that minimizes this quadratic, which has to do with the square of the, what has to do with the Hessian. This is the Hessian around the optimal solution. So it's a value of u that, it's a value of u that minimizes u times basically the quadratic approximation of the objective at the optimum with u. So this would be the linear term, and this is the quadratic term associated with the optimal solution. And then basically this is feasibility and complementarity of the u's at optimality. So I get an optimal solution and then feasibility and complementarity. Okay, so so this is a little bit different from the central limit theorem. It says it converges to something that's an optimal solution of this other mathematical program. Oh, and part of the objective coefficient in here is normally distributed. So where u gets its distribution is through the objective. So there's a set of constraints that it has to satisfy, and then a normally distributed objective. Effectively, what it's like is, if there were no constraints, I would have the central limit theorem. I would just have like an elliptical distribution around the true optimal solution, and my x nu is going to be distributed with that elliptical distribution. But because of the constraints, what it's like is I take that elliptical distribution and I project it onto the set of constraints. So what this program does is it basically is projecting that solution onto the set of constraints. And I'll show you an example to illustrate that. So here's the example. So the feasible region is just a to infinity. So and a could either be less than 0, 0, or positive. And xi is normally distributed, and it's just x minus xi. Well, xi is normally distributed. It's a standard normal, so it has mean 0 and variance 1. So this would be my expression for the objective. So this is just the standard normal density, and I'm just taking the expectation of that. Okay, so the optimal solution should be, I'm just trying to minimize the difference between x and xi. So it should be 0 if I don't have any constraints. And if a is negative. So if a is negative, it will be 0. If a is 0, it should be 0. And if a is positive, it should be whatever a is. So the optimal solution, if a is greater than or equal to 0, is always a. And if a is less than 0, it'll be 0. So if I set up that problem that was on the previous page, then C actually is going to be normally distributed with mean 0 and variance 4. So we'll have standard deviation of 2. And then my U that satisfies this is going to be 0 if A is positive. And if A is 0, then what the solution is going to be, it's going to depend on the sign of C. So if C is negative, then I'll try to make U large. U will be greater than 0. But if C is positive, then I'll make U 0. So half the time, I'm going to have, I'll have a mass at 0. So with probably 1/2, I'm at 0. And with probably 1/2, I'm on the positive part of basically on a truncated normal distribution. The normal distribution for positive values, or the positive part of the normal distribution. Okay, so that, it's hard to see. But this is just, when A is negative, it converges to a standard normal. When A is 0, it converges to something that has an atom here with probability 1/2 at 0. And then the positive part of a standard normal distribution. And if A is positive, it converges to a point. So it converges exactly to A. So this is very fast convergence. So this is faster than the central limit theorem. This says it converges to a point, not just to a distribution. So it asymptotically just goes to that point. That says with finite number of samples, then you'll get an exact optimal solution with probability 1. But this is the thing that's different. So usually in the central limit theorem, we just end up with a normal distribution. Because of the constraint, we project everything onto the constraint. So here's that constraint. So often we get these projections. So we'll have some atom that's associated with the constraint, and then some projection onto that constraint. And sometimes we'll just end up with a single point. Oh, yeah. So an atom would be a point that has positive probability as opposed to like where there's continuous distribution. So it's a point in the distribution that has, so it has positive probability. So this one is everywhere over here, because it's continuous, I just have a density. So at any given point, basically the probability is 0. But when I go over any interval, I get positive probability. So I have to go over intervals here. But here, at a specific point, I actually have positive probability. So I have probability 1/2 at that point. Okay, so I mentioned these cut samples last time. So I'll mention how you can improve them by using something called importance sampling. So importance sampling is this idea that I'm trying to approximate this function up here, but it may be hard to evaluate this, and this may have very high variance. So when I try to sample from this distribution, like if f is the density in this case, this is my recourse function. When I try to sample from this distribution, it may have very high variance. So what I can try to do, if I have an idea about what the value might be, I'll use a different density. So I'll convert from this problem to using another density g by just multiplying by g divided by g. So then I'm sampling this, which is be my original q times f divided by g. So instead of sampling q, I sample q times f divided by g. And my samples are drawn with respect to g. So the function that I'm sampling is this qf divided by g. The idea of this is if g was something like, if I could actually take q times f divided by the expectation of this, then every single sample would be the expectation. So just one sample would give me the true value. So if I can get g to be close to whatever this true distribution is, then with a single sample, I can get a true value. So that's the idea of importance sampling. If I can get g to be pretty close to whatever this value is precisely, but I can estimate this better than I can just q times f. Well, that gives me much lower variance when I take samples. So one thing we do to approximate in these two-stage models is I'll say, well, what's the best separable approximation? So I'll try to separate out I'll try to break my original q into components that depend on each of the different components of the vector c. So I'll substitute in such that I have different components that depend on each of the individual values of c. So I'd have one thing that depends on C1 and one that depends on C2. And I can sample from those because they just involve single integrals. So it's easier if I can just deal with one variable at a time. So this function that just has, this would just be one variable, just ci, can't see the I, ci just one at a time. It will be easier for me to just sample from each of them separately. So this is, I go in, I'll start out at the mean and then go in coordinate directions away from the mean, and then use those coordinate direction values as my function g, and be able to evaluate what happens to the function along those coordinate directions, and then use that as my function g that I sample from. yeah, so as I said, sometimes you have issues with convergence, but let me talk about this last set of algorithms. So this algorithm, this SDDP, I'll talk more about applications tomorrow, but this has been used now for more than 25 years by Pereira. Well, it was originally Pereira and Pinto, and what they did is they took my nested decomposition method, and they said, well, what we can do is add sampling. So they took that nested decomposition method and said, let's add samples into it. And we'll make a few assumptions, but we'll try to use sampling to be able to solve very large problems. And they use it to solve very large problems for electric power companies. So they started out in Brazil, but I don't know how many countries, but probably more than 40, 50 countries now use this method for scheduling electric power generation. And so it's become very, very, very popular in the power industry because it's able to solve particular problems where there's things that last over a long time, like water reservoirs. So particularly for water reservoirs, this has been used very extensively. Okay, so the assumptions in this method that we have relatively complete recourse, which means there's always a feasible solution in the future. You don't need any feasibility cuts. And serial independence, meaning that the realizations in the future are independent of any outcome right now. So at every point in time, there's an independent probability to say that I'm going to get a heavy rainfall next month. That's independent of what the rainfall is this month. And so their assumptions are that I have this kind of serial independence plus relatively complete recourse. And the idea of the method is basically I have a tree of all these scenarios, but there's many, many of them. So there could be literally billions. So there are going to be billions of these. Often these are applied, like I said, in these hydropower problems where the decisions are made weekly. So there would be 52 stages, and in every stage there would be maybe 1,000 scenarios. So you'd have 1,000 to the power 52, which is, that's an astronomical number. 10 to 150th, okay. 10 to 150th possible samples, which obviously is going to be too large to put into a single problem. What they do is they sample from the sample paths. So they sample out of those 10 to the 150th sample paths. They'll sample maybe 100 or 1,000. So maybe we'll sample 1,000 out of those 10 to the 150th. And along each of these sample paths, we're going to come up with a solution. Now, the solution is going to be based on an approximation that I've built. So I'm always going to have an approximation of the value function. And I'll use that approximation, whatever approximation I have at every point. It's always going to be a lower bound. So in each one of these sampled scenarios, I'll get a lower bound. So I'll get a lower bound, and I'll get a value for using each of these. Well, actually, along each of these, I'll get lower bounds, but I'll also get an upper bound by saying, well, this is going to be a sample of what my actual solutions are going to be. So I'll get an upper bound, which is a sample of what my actual values are going to be. And then at every stage of the model, I'm going to solve a lower bounding problem to get a lower bound. So I'll have like the Cx plus theta value that I had in the nested decomposition or in the decomposition method or L-shaped method. So I get a lower bound and an upper bound. I sample these two, and if those two samples, those upper and lower bounds, are close enough, then I'll say I've converged. It's simpler than the nested decomposition in that it eliminates a large portion of the tree in the forward pass. In the backward pass, basically now for each one of the points that's along one of these sample paths, I have to find a set of cuts. So I have to solve all the samples that come out of this. So I'd have to solve 1,000 problems out of this, 1,000 problems out of this. You'll have to solve 1,000 problems out of each one to get new cuts. But you can use those cuts everywhere in the tree. So every time I'm solving one of these, I can use it everywhere else to create my lower bounds. So I get lower bounds. So I sample going forward, I get an upper bound. I go back, create those cuts to get lower bounds, and then I repeat this process until I get convergence. Yeah. How do you have? Yeah, so I use a couple of different methods. So you can use pseudo-random numbers. So normally you would, well, so for normal, normal you can convert to polar coordinates, and then you can take uniform in the polar coordinate, and that gives you a normal distribution over the sphere. So for normal distribution, you can just do the polar projection. Yeah. Yeah, so for normal distribution is nice because the normal distribution just corresponds to sampling over the sphere. So I just, like it's, yeah, any point in the sphere, and that gives you a normal distribution. Yeah. Yeah, so that one, so yeah, you take the unit sphere, and then, I mean, you can always, but for standard normal, take the unit sphere and then sample over that, and that gives you standard normal distribution, even multivariate normal distribution. Yeah. Let's see, how do you do that? I think you have to do it. Yeah, I think yeah. So you have to do sample from the sphere, and then take the normal, then invert the normal over the line. I think maybe that's it. Yeah, sample from the sphere and then invert it over the line. But the inversion, normally what you do is you just do F inverse of uniform, and uniforms within 0, 1. Now, to do the uniform within 0, 1, what most people do is they use these pseudo-random numbers, which are, basically they're made to satisfy properties that random numbers would satisfy. So they satisfy all the tests for a random series. So it's a deterministic sequence of numbers, but it satisfies, like if I do a test on, is this a random sequence of numbers, it will satisfy that test. So as long as it satisfies that test, I can do it. There are some other ways. You could use quasi-random numbers. The ones that I like are sort of simple to construct. The ith quasi-random number is you take something like the square root of I, and then subtract off the floor of the square root of I. So in other words, to get a number that's quasi-random in 0, 1, you take the square root of each I, so like I is, I guess it goes 2, 3. No, actually you have to use primes, sorry. It's got to be 2, 3, 5, 7, 11, 13. So you take the primes, take their square root, and then subtract off the integer part. And so this sequence of the fractional expansion of the prime, because it's a prime number, it never repeats. So it never repeats as you have different prime numbers. And so it has to end up looking like uniform over 0, 1. So if you take the expansion of the, take the expansion of the fractional part of the square root of every prime, that gives you a sequence that ends up looking 0, 1. So that one, I like that one in particular. Okay, let me, this is just illustrating that. This is an algorithm that actually, that I've worked on that speeds up the SDDP basically by, you don't need to do all this, look at all the possible samples going forward. You can sort of reduce the number of samples that you look at. And that leads to some faster convergence. So you only have a limited number of cuts. And overall, these methods converge, again, with a finite number of samples in every time period. It's just some computational results. I was just comparing to the SDDP. Our other method called AND, or bridge nest decomposition, does pretty well. So these are SDDP times. I'll talk about what these are vehicle routing problems. I'll talk about those tomorrow too, but this is just showing you the time that it takes for this bridge nest decomposition to solve these problems. Okay, so what I did today, I talked about the stochastic gradient methods. The step size has to decrease at a given rate, like 1 over t for t iterations. These sample average approximations also converge, and they converge exponentially fast, and sometimes in a finite number of samples. So we get fast convergence from these methods. But you have to be careful because it's very easy to be tricked into stopping early. So you really have to increase the number of samples that you take. If you're going to sequentially test, then each time you test, you have to have more and more samples. And applying it with the decomposition methods, as I said yesterday, you have to be careful because you could often end up converging to the wrong solution unless you really make very precise the cuts that you generate. Okay. And I have some exercises that use these different methods that you can go over in the session tutorial. Any questions? Okay, thanks.